Hi students. Okay, we are chapter 7 in our 12th chapter series in Psych 218, Analysis of Behavioral Data. In this chapter, we're looking at probability in samples, specifically the distribution of sample means. What this means is that instead of looking at a distribution of raw scores, now we're going to take the sample means from each sample, put them in a distribution, and we get a distribution of sample means. Now, if you are confused by this, we're going to explain that using pictures in a minute. But let's go through the slides first. Again, take a moment if you are struggling with this concept. Think about the difference between a distribution of scores and the distribution of means. So far we've looked at distributions, and they could be, and they usually are for us, normally distributed. So it can have a population mean and a population standard deviation, and inside these distributions are scores. You're going to have many of these x's, x1, x2, x3, and whatnot. And then because we don't always get to work with the population, in fact we rarely do, especially when we look at large populations, we often work with samples. So instead of population mean and population standard deviation, we'll work with samples. And the sample has its own set of raw scores, its own mean, and its own standard deviation. Now, how would we use sample data to make estimates about the population if we can rarely, if ever, measure large populations at once, like trying to ask thousands of people or millions of people? Often we can only ask, tens or hundreds of people at a time. So you may think about this if you're taking a research methods class in Alexander College. It will be Psych 217. You might do a survey for 20, 30 people. But your question, as in research question, might be asking about populations like psychology students or college students or international students. So how would we approximate this population using a sample of, 20 or 30? So this is where this chapter comes in, and that's the foundation of this chapter, answering the question, how can we use sample data in a way that we can estimate a population? Again, just one sample isn't going to do it. We're probably going to need more samples. How many would you need? Well, eventually you're going to think, I'm going to need lots of samples. And there's a way of doing this. So for each sample, we would get a sample mean. And then if we put those means in as a distribution of sample means, it will have its own distribution with its own mean of sample means. And it will have its own standard deviation of sample means. And this is going to be called the sampling distribution. And that's the distribution of sample means. So this distribution right here is what we're going to look at today. In terms of learning outcomes, first thing we want to do is to define the distribution of sample means, describe the sampling distribution by its shape, its expected value, and its standard error. Standard error here is the standard deviation of the sampling distribution of means. For the context of this course and for most sampling distributions, we would use sampling distribution of means. Number 3, we want to describe the location of the sample mean, M, using z-scores in the sampling distribution. And finally, we want to determine probabilities. Again, that's why we did chapter 6. We need to know how to do probabilities in distributions first. in order for us to figure out the probabilities that corresponds to a sample mean using z-scores in the unit normal table. So the third outcome, you can think back to chapter 5, and for the fourth outcome, you can think back to chapter 6. The math tools you'll need, again, mainly come from your previous 2 chapters in this course. So the one right before is random sampling and probability, why we need to do this and how this would work for us. Because the sampling distribution involves the sampling technique, we need to use the right sampling technique to get the right samples for the sampling distribution to work. So you can review that in terms of chapter 6, how we get those random samples. We need z-scores as well from chapter 5 because we'll be working with normal distributions and z-scores. And also we're going to work with probability to find the location of a sample mean and its proportion, either above or below that sample mean in that sampling distribution. Okay, so we're going to need chapters 5 and 6 respectively. So let's start with the story of the sampling distribution. Again, we work with 2 things, 2 distributions. And they are the population that we have questions about and the samples from which we get groups of people from that larger population to find answers to those questions. Again, those questions can be things like, probably heard them by now, could be what's your body temperature, what's the expected GPA, what's the expected hours of sleep, and so on. Again, we can't ask everybody, going to assume that, but you could ask tens or hundreds of people. So how would we make the connection between sample and population? So far we know that if we have a score, and these are raw scores in a sample, we can mark its location in the population. If we know the population mean and standard deviation, then we can put that raw score into a z-score. So it's going to change from an x to a z. Often though, when we do research, just like in the first 2 to 3 chapters, we tend to study entire samples rather than single scores. Well, think about it. Often the questions we ask about more than one person. If you just want to ask one person, all you have to do is go to that person and ask them, hey, what did you get on the test? But if you want to know like the average, you're going to need to ask more than one person. If you want to know how people generally feel about things or how people generally respond to things, you're going to want more than one person, more than one score. So this is what the second point means. We tend to study entire samples. So that's why we get values of central tendency like average and measures of variability like standard deviation. Therefore, the samples in a way provide an estimate of the population. However, it is a biased estimate because the sample is always going to be smaller than the population, often much smaller, and the values tend to be more extreme. And if it's random sampling, you're going to get values that tend to be closer to the mean with less variability. So the bias is there in terms of estimating the population, and we need to address that. If we want to do hypothesis testing, which is the next chapter, as we, try to make decisions about our research questions, whether samples are the same as the population or one sample is different from another, we need to find some way to transform the sample means that we get. Again, we're less interested in individual scores because, again, we're asking groups of people and we want values that represent samples, not scores. And we want to transform those means into some z-scores. So we need some way to connect a sample distribution, again, using statistics here, English letters like M and S, and here it would be a sample, and connect it to some way in some way with a population distribution, which we might not have access to, and often we don't. So in between this process, we're going to use something called a sampling distribution, where we grab the means, and we do this, and spoiler alert here, you're going to do this potentially infinite number of times, and then you'll have a distribution of sample means, and then it will have its own mean of means and its own standard deviation of sample means. And this is the distribution that we're going to use to approximate the population distribution for us to do hypothesis tests. Of course, if you happen to have a population distribution, then you would use that logically, but chances are we don't. So again, the next slide talks about sampling error. This term should not be new to you if you have, reviewed chapter 2 where we talk about sampling error, and if you looked at it in chapter 4 where we talk about standard deviation and variance for samples, we address this using degrees of freedom to increase our estimate of variability where the sampling error reduces that variability. So here, the error in this does not mean you made a mistake, but it's a discrepancy. It's because we're grabbing fewer people, and because the people we tend to grab from the population would be closer to the mean, and it would be less variable. And the samples themselves often are never the same, especially if everyone has an equal chance of being selected. So again, there are differences between the population to one sample to another sample to yet other samples. So before we go to slide number 6, the distribution of sample means, let me demonstrate this in terms of sample error. And we'll use a small distribution of, let's say, 4 people. So very simple. We got 4 scores. And this is our population of 4 people. Now, if you happen to know all 4 scores, okay, then you'll be working with the entire population, and you'd know stuff like, oh, well, the mean here is 10/4, which is 2.5. And you can calculate the standard deviation as well if you wanted to. Okay, so you can take a moment and calculate that if you want. So if you do your math, it'll be 1.12. Sum of squares is 5, and then the variance is 1.25, and then the square root of that for standard deviation would be 1.12. But the number we're interested right here is going to be the population mean. And if we grab samples of this, obviously we could grab a sample of 1, but we wouldn't. But think about it. Each time you grab a number, you can only do this 4 times. You would grab 1, 2, 3, or 4. And each one of these is not the same as the population mean, the expected value in that pop. So if we go a sample of 1, then you're going to get 1, 2, 3, or 4. That's it, really. And each of these values is not the same. They are not the same as 2.5, which is the population mean. You could go for a larger sample. So here we grab 2 people. Getting a little closer. So here we're going to go do our different combinations. So 1 and 2. 1 and 3. 1 and 4. 2 and 3. 2 and 4. 3 and 4. And that's kind of it. Let me see if there are any other ones. 1, 1, 2, 1, 3, 1, 4, 2, 2, 3, 2, 4, 2, 1's already covered. Okay, 3, well, there's 3, 1 already, and 3, 2, so the only thing left is 3, 4. So if we do, now we can start doing averages because we have more than one value. So here the mean would be, well, 1.5. Here would be 2. Here would be, well, we finally get a 2.5 here. Here's another 2.5. Here's, well, 3. And here is going to be 3.5. So using a sample of more than one person, now we can start seeing some things in terms of sampling error. As you can see, when we use samples and not populations, again, we are not getting everybody. And the larger the sample, the closer or more representative it is to the population. But no matter how large the sample is, as long as it's not the population, the values that you're going to get, starting with the mean, is not going to be the same. And even if they have the same values, like here for sample size 2, 1 and 4, 2 and 3, well, they come out the same in terms of the sample mean, but that's only 2 out of 6 samples. And the scores within which you use to calculate the mean, they're not the same. You only have 1 and 4 or 2 and 3, but the population has 1, 2, 3, 4. With a sample size of 3, that gets more interesting. I'm going to need more space for this. So 1, 2, 3, 1, 3, 4. I'm going to do better combinations here. 1, 2, 4, 1, 3, 4. And that should cover everything. 2, 3, 4. So we're going to use extra space to calculate these means. So here, well, it's 6. So the mean here is 3. And here is 7. So it's going to be 7 over 3. This is going to be more interesting. 8 over 3. And then here, actually, big mistake there. 6 over 3, which is 2. And here, well, it's 9 over 3, and this is 3. Again, different sample size, and also none of these really are the same as 2.5 either. So that's what we talk about when we talk about sampling error. Notice that with the different samples we use, as long as it's not the population, even for a small population of 4, you can see that the expected values that we're going to get are not the same as the population mean. Even if you get the same sample mean somehow, again, the data is going to be different. That's sampling error. And notice here, if we do standard deviations for anything that is a sample of 2 or more, then we can also see that your S values for these guys are not going to be the same as your population standard deviation either. Again, as the sample gets larger, the variability gets less. So that's sampling error. And we're going to continue with this example to show you how, once you collected all the samples you can, and as the samples get larger, you're going to need more sampling. You're going to need more samples. And so with larger sample sizes, you're going to reach infinity number of samples and then start using the sample means, make a sampling distribution to form a sampling distribution of means, where you can start approximating population mean and looking at standard deviation of the sampling distribution, which would be standard error. Okay. So let's begin. So the story continues. We know when we use samples, we will get sample error. The statistics are going to be different from the parameters. That is, the sample means are going to be different from your population mean. You can have multiple sample means, but only one population mean. And the samples themselves differ from each other. So, using that fact, we can apply it to a technique where we collect a distribution of sample means, where we do all the possible random samples of a particular size that we can, and then make that as a distribution of sample means, and then that distribution of sample means is going to be a much better estimation of the population than any individual sample out there. And before a demonstration, this is the last point that will come back to you as we do the demonstration. So remember that when we work with sample distributions, they are just raw scores. But when you put them together and you make a sample mean, and then you do this for every sample, and you get sample means, and you put them in a distribution, then it's a distribution of sample means. So at this point, I'm going to demonstrate it to you now. So here is one that I made before using a population of size 5. And this was done in a virtual class. And this demonstration would take about 10 to 15 minutes. So you can pause the video at this point and see how it's done. It's just like the one we did for a population of 4, and we start grabbing samples of 1, 2, and 3. So for the purpose of this video, we're going to use that. So again, we have a small population. Here it's going to be just of x's. You have 1, 2, 3, and 4. And we know things like, oh, okay, this has a mean of 2.5, and this population standard deviation of 1.12, which was the square root of 1.25. Again, the value we're interested in right now is the 2.5 for the population mean. Again, we could grab samples. So we can have 1, 2, 3, or 4. That's it. You can only grab 4 samples of 1. With a sample of 2, we can do more. We can grab 1, 2, 1, 3, 1, 4, 2, 3, and 2, 4, and then 3, 4. Here we can grab 1, 2, 3, 4, 5, 6 samples. Yes, compared to 4 samples. And each one of these would have its own mean. So here the first mean is going to be, well, 3 over 2, so that's 1.5. So our next mean, and I'm using x bars here, 2, here's the next one, is 5 over 2. So again, we can calculate the sample mean for all of these. So this is our 5th sample, and this is our 6th sample. That's 7 over 2, which is 3.5. And then we could do this one more time if we wanted to. Okay, let's say we have a sample size of 3 this time. So how many samples can we have? 1, 2, 3. Okay. 1, 2, 4. Okay. 1, 3, 4. And then 2, 3, 4. Okay, for these, we would have, okay, 6 over 3. Okay, that's 2. And then we do it again. Here is 7 over 3. Okay, which is, 2 1/3. Okay. Here, our third sample, 8 over 3, which is 2 2/3. And then here, the last one. Okay, it's 9 over 3, which is, well, 3. So you might start noticing something. If you did the averages of these guys, they would all come back with the same result. Again, with the sample of 1, well, that means you grabbed everybody. Remember, the technique here for sampling distribution is that you grab all the samples you could. And that's the theory here. So if you only have the sample of 1, well, that means, well, that's no different than asking your population. Again, it's not entirely possible, but the theory makes sense. So you still get a mean of, well, 10 over 4. Okay, so this would be your mean of x's here. So then you'll still be 2.5, which is the same value as your population mean. Now, the other distributions of different sample sizes are going to be more interesting. So here you can see, and we can actually draw these if we wanted to. So notice that you have these values. You have 1.5 plus 2 plus 2.5 plus 2.5 plus 3 and then plus 3.5. Okay. And then you had 6 samples in here, so you divide that by 6. So you can take a moment and figure out what the average is for this. And you'd know it's still going to be, you can probably guess, 2.5. Well, let's see for sure. So here we can go, okay, 3.5 plus, well, 5 plus 6.5. Okay, divided by 6. So far, so good. Okay, is 10 plus 5 over 6. Okay, is 15 over 6. Okay, and we can simplify. It's 5 over 2, which is, 2.5, which is the same as the population mean. Here you notice that instead of working with 1, 2, 3, and 4, now we're working with sample means. If we were to use notation, this would be your x bar 1 plus x bar 2 and so on plus x bar 6 and then divided by the number of samples, right, which is 6. You could use sigma notation if you wanted to, x bars, and then you divide it by the sample. And we'll do this one more time. Again, so the values we're using, which is sample means, is the thing we use to make our sampling distribution. So anything below this line right here, and once we started calculating sample means and use those to make distributions, we are making sampling distributions. So we can do this one more time. Here, we'll put in our values. 2 1/3, 2 2/3, and then plus 3, and then divide that by, well, we had 4 samples, so that's 4. Well, let's take a look. All right, so it's 2 plus, well, here's 5 plus 3, and then 4, what's 10 over 4? 2 over 5, which is 2.5, which is the same as the population mean. Notice that with sampling distributions, As long as we collect every sample that we can using random sampling, where every score here from the population has an equal chance of being selected as a sample, which means I'm going to do everything, every possible combination. And for each combination, determined by its sample size. So here for the middle column, I got sample size 2. And here in the third column, I got sample size 3. Then, as long as you add all the sample means together and divide it by the number of samples you use, you form a sampling distribution where you can start calculating the mean of the sampling distribution of means. So in this case, I want to let you know as well and remind you that you can get a sampling distribution of anything. You can, as long as you get the sampling technique, as long as you get sample data for each sample, and as long as you do make some calculation, you could calculate medians if you wanted to. You can calculate modes if you wanted to. But for this course, in this chapter, and for most statistics, we're going to use the sampling distribution of means, because we're using data that is interval ratio, and the mean is probably the best measure of central tendency for this purpose. So this is our sample or sampling distribution and how it works. So another demonstration then would be something like this. Here is another one where you have values of 2, 4, 6, and 8. Again, there are 4 scores. You can do the same thing again. If you know that, okay, I got my x's, and they are 2 plus 4 plus 6 plus 8. Okay, well, I can calculate the population mean. That's simple enough. And this, for now, we assume it's a population distribution. So then, okay, well, let's take a look. It's 20 over 4. Well, that's 5. Again, you can make samples of 1, 2, 3, or 4. Well, with 1, it's kind of redundant. But once you start making samples of 2 or 3, then you can do the same process that we've just done with our small population of 4. I just use 1, 2, 3, 4. Here it's 2, 4, 6, 8. And you can practice and see for yourself what would happen. In the next slide, here is an example, a visual representation of what would happen. So each of these blocks would be an X bar, a sample mean. So in this case, you could get a number of sample means and so on. And then eventually you'd notice that, yeah, this distribution of sample means, this sampling distribution of sample means would have the same value for its mean, which is 5, as the population mean. Its variance and standard deviation in the sampling distribution would be different, but the mean of the sampling distribution of means, that value would have the same value of the population mean. And that's why we do this technique. We want some way for us to make reliable, consistent, and accurate estimations about the population using samples. And since we can't do it with samples, well, we use sampling distributions. So this next slide here talks about this point. As long as you collect all the sample means from each possible sample and you make them into a distribution, then the sample means would pile up around the population mean. And so on. And then this distribution of sample means would be approximately equal in shape because you make a potentially infinite number of samples, but definitely all the samples that you can get, depending on how large the population is, how large your sample size is when you want to make your sampling technique, which would determine how many times you need to do it. But you need to do it for every single possible combination. So again, it's potentially infinite. But with small populations like 4 or 5 people, and we apply the same technique, well, we can use the math to calculate it a lot easier because, well, you just need to do it 6 times for a sample of 4, for a sample of 2 if the population is 4, for example. But again, the distribution would be normal in shape, approximately something like slide 19. And so the mathematical concept for this is the central limit theorem, is that as your sample means pile up, as you do more and more of these samples, as long as you do them all, n approaches infinity, because you're going to do this more and more as long as you do them all. Again, if your population's huge, like 7 digits, 6 zeros, that's like 1,000,000, and if you collect a sample of 20, you can figure out in terms of probability. So population size, and then here you got your sample n equals 20. Well, how many times are you going to grab 20 people using random sampling out of 1,000,000 people? So again, as n approaches infinity, as you make these samples with its own mean and its own standard deviation, as you do this potentially infinite number of times, as long as you do all of it, every possible combination, the theorem goes, as n here, the number of samples you collect given a particular sample size from the same population, then the distribution of sample means would have its own mean, here designated as mu m. Here it's the mean of means. So you think of this as the mean of sample means. And it would have its own standard deviation. And there's a term for this called the standard error, because this reflects sampling error, because we're collecting samples. And there's still variability in the sample means, because we're grabbing from different parts of the population. But another term for this would be the standard deviation of the distribution of sample means. So the sampling distribution is a normal distribution that is formed as the number of samples you use approaches infinity. It will be its own distribution that is normally distributed with its own mean of sample means, which equals the population mean, and it has its own standard deviation, which is its own value. As n gets larger, though, the standard error, that is the standard deviation of sample means, is going to be smaller. And we'll cover that as well when we do more on standard error. So in terms of the shape of the sampling distribution, as you start collecting samples that is larger, and you do the same process where you collect sample means, then a couple things would happen. If you select samples from a population that is normally distributed, and you collect samples where the sample size is pretty large, like 30 or more, then the sampling distribution of sample means So a good reminder here is that when you see sampling distribution, it's a distribution of sample means. If you see sample distribution, it's a sample distribution of raw scores, or sample distribution of scores. The sampling distribution of sample means, or the distribution of sample means, would be close to perfectly normal. It would pile up in the middle with its sample means. It would have its own mean of sample means and its own standard error. That is the standard deviation of the distribution of sample means. Okay? And this shape of this distribution, when the distribution of the population itself is normally distributed, where you grab the sample from, and the sample size is large enough, at least 30, then it would be relatively normally distributed. Again, as sample size gets smaller, the distribution would be fatter and flatter because you'll be getting more extreme values and the means will be more extreme. So I'll show you this later on in the same demonstration. But for now, let's go to our expected values of the distribution as we continue to talk about the sampling distribution. Here, first we talk about central tendency, and that is the expected value of M. So just like we can get expected values of scores, because now we're making a distribution of sample means, then we can have a value of central tendency and expected value of these sample means. And that expected value then would be equal to the population mean. Which is good news for us because now we have a distribution that is the distribution of sample means, or the sampling distribution of sample means, that we can use to approximate the population distribution without having to actually ask the population. As long as we apply that central limit theorem, as long as we apply the technique of sampling distribution, then we can find what the population mean is, which is good news for us because we need to compare the sample to the population mean if we want to compare samples with the population. So this expected value of M, this mean of sample means, would be crucial for us as a reference point. And this statistic then, unlike any of the sample means out there, that's going to be the unbiased statistic. Next, another property of the sampling distribution of means is its variability. That is its standard deviation, or here specifically the term is standard error, which reflects the sampling error that is there when you collect samples from the population. So here again, the standard error is the standard deviation of the distribution of sample means. So this is what this part says right here. And the standard error in this case of M, which is means, provides a measure of how much distance each sample mean is expected to be between the sample mean itself from the population mean. And we have established already that the mean of the distribution of sample means is the same as the population mean. So then we can use that for us to compare the distance between each sample mean in this distribution of sample means, be it, the first one, the second one, the third one, whatever. And we can compare that between a sample mean and the population mean. And once we do that, getting its own standard deviation using sum of squares and variance, then we have standard error. That is the standard deviation of the distribution of means. So to review, then, your sampling distribution would have a distribution of sample means it would have its own mean of means, which we have established at this point that it's the same as the population mean, and its own standard deviation, which is standard error. It is not the same as the population standard deviation. It cannot be, because again, the process from which we get from the sample means we're not using everyone, so there is sampling error. And then the distribution is a distribution of sample means, not sample scores, not even population scores. Even though you would get all the scores in your calculation under the central limit theorem, but then the scores we're working with are sample means. They're not the scores anymore. They're statistics now, not raw scores. So again, the mean of the distribution of sample means is the same as the population mean, but the standard error is not the same as the population standard deviation. Now, here's something that's interesting about standard error. As the sample size increases, the standard deviation of the sample means distribution, or the distribution of sample means, or the sampling distribution of sample means, whichever term you prefer. I would assume you prefer the shorter term, but it's good to know what it actually is. So the full name would be the standard deviation of the sampling distribution of sample means. But here though, the law of large numbers says the larger the sample size, the more likely it is that the sample mean would be closer to the population mean. Again, we can use our previous example to demonstrate this. Notice here, again, we have a population mean of 2.5 in this sample of 4 people with each a unique score, 1, 2, 3, or 4. Notice in the smallest sample we can do, 1. Again, you can get any value, 1, 2, 3, or 4, and none of those are from the mean, and they're really far apart, like 1 from 2.5, and then 4 from 2.5. That's the largest spread you can get, like a sample of 1. Still, as you notice, even in terms of range, which can help us, predict the standard deviation, you notice that here we have a range of 3. And you notice it's the same, standard deviation, but as samples, then you would, use standard deviations for these guys, so samples of 2. But notice here, for each of these means, here, for sample of 1, you get the full range and the full standard deviation, 1.12. Here, though, you notice that the smallest value is no longer 1 in the sample size of 2. It's actually 1.5. And the largest value in terms of means here is 3.5. And so, yeah, as the sample size gets larger, the distribution of sample means gets tighter. So the range here is now no longer 3, but 2. And therefore, the standard deviation of this sampling distribution is going to be smaller than this one, than the first sampling distribution of just 1 sample. Here in this sampling distribution of a sample size of 2, you see the range of this distribution and the standard deviation is smaller. And let's go to the third sampling distribution. Here we have a sampling distribution of means where the sample size is 3, and the smallest mean here is 2. Whereas the largest mean here is 3. Again, we're using all the possible combinations with this small sample size. Notice now, instead of a range of 2, you have a range of 1. And therefore, the standard deviation is going to be smaller yet again, because the distance of these sample means from the population mean, which we have established is the same value as the mean of sample means, then you can see, oh, yeah, as the sample size gets larger, the the standard deviation of the sample means, or the standard error, gets smaller and smaller and smaller. So range is easier to calculate, so I'll use that instead for the sake of this one. But you should know that the relationship between range and standard deviation, as range gets smaller, so does standard deviation. So range here is 2. Here the range of this guy is 3. And here the range of this guy is 1. So standard deviation is going to be even smaller than this. And one thing I'd like you to think about, if we, increase the sample size of even more, although technically it's no longer a sample because you grabbed everybody, if you use 4 each time, so you can do 1, 2, 3, 4, do it in different order, like 4, 3, 2, 1, whatever, and work with the permutations. Each time, you're going to get 2.5, 2.5, 2.5. And so the variability here is going to be 0 because you're getting the mean every time. The range is going to be 0. The standard deviation is going to be 0 because it's 2.5 minus 2.5 each time. The deviation score is going to be 0. Doesn't take much time for you to go, oh yeah, if there's no deviation, then there's no standard deviation. So again, the larger the sample size, this law of large numbers, the smaller the variability is going to be. Smaller range, smaller standard deviation, and here is referring to the sampling distribution. Therefore, the standard deviation of the sampling distribution as n gets larger, when you do your sampling distribution, the standard error is going to be smaller. So that's what that's about. Also, another property is that if the population itself is tighter, that is, the variance of the population is smaller, then also you can go, oh yeah, the sample mean from that this population distribution would have also a smaller variance. So I can demonstrate this as well relatively quickly. So remember here, in this population, I use the scores 1, 2, 3, and 4. That has its own standard deviation, and I can square that and give me 1.25. That's its variance. So if we did the same thing for a different population where it's larger in variance, let's say this one, instead of a population, and then use this population 1 here, where it is 1, 2, 3, and 4, and then this one, population 2, which is what we're looking at in the slide, 2, 4, 6, 8. Notice here, we have multiplied the scores of population 1 with a constant of 2. Therefore, the scores are wider apart, and therefore, whenever we select the score for our sample, no matter what size, again, the larger the population variance is, the larger the sample variance is going to be when you use the same sampling technique, that is random sampling. If you use a population distribution with a smaller variance, then you're going to get samples that is also going to have lower variability. That means your distribution of sample means is also going to have less variability. That also means that standard error is going to be smaller as well. So not only does the sample size influence your standard error, the population variance itself, be it known or unknown, would also affect standard error. Less directly than your sample size, because sample size is within the researcher's control, whereas the population itself, not so much. So going back here, to standard error. We reviewed this and we talked about how the standard error can change in magnitude, again in sample size and in population variance. So here is a graph of this. So if we somehow know several things for this exercise, if we know that the population standard deviation is 10, and we collect sample means and makes a sampling distribution. So here we got a sample size of 1, obviously is going to be the same. The standard error of a sample size of 1 in its sampling distribution is going to have the same standard error as the population standard deviation. However, as you get a larger sample size, there's an inverse relationship here that your standard error is going to get smaller and smaller and smaller until eventually, if you happen to grab everybody, it approaches 0 in terms of standard error. But notice here, as you increase your sample size, your standard error decreases. There's a mathematical relationship for it, but it's not covered in this class. But you can figure out what it is once you see the standard error formula. It involves square rooting, an inverse square root of the sample size. Here are some more pictures showing you the comparison between a distribution of scores and a distribution of means. Again, a distribution of scores here would be either a sample distribution, which is what we're going to work with, or a population distribution. Because these are the only distributions, right now we're talking about sample and population distributions, that deal with scores, that contain scores. However, when we talk about distribution of means, that's a sampling distribution, where we collect a mean from a sample each time we collect a sample, and we do this as many times as needed, getting every possible combination of samples. So here you notice that, in distribution A, you see the original population distribution of IQ scores. It has a mean of 100 and a standard deviation of 15. You get a sample distribution of 25 people, and you get their scores. And that sample distribution, this is just one of them, has a mean of 101. Again, because the population distribution of IQ scores, is normally distributed, and the sample size is quite large, and the population itself is also large and normally distributed, you're likely to get a sample mean which is close to the population mean here. Notice that, the sample mean is 101. Again, not the same as your population mean, but it's close. Your standard deviation here is smaller for the sample. Again, because you're going to get scores that's closest to the mean. That's part of sampling error or sample error. But if you do this a number of times and, your sample size is 25, notice your standard error, once you calculate it, it's no longer 15 in the sampling distribution. In distribution C, we're looking at the sampling distribution of sample means that is collected from your population of IQ scores each time it's 25 people. So it would have the same mean of means, which is 100, so it's no longer 101, because all these averages, pile up, and then you average those averages, you get 100 again. Again, under the central limit theorem, where you get everybody. Or all the samples, I should say. That is possible. And then, because those scores pile up, and those scores are, again, closer to the mean than the population scores themselves, the standard error, or the standard deviation of the sampling distribution, is smaller by definition, because these are sample means, which are closer than to the population mean than the scores themselves. Now, because we are working with a normal distribution, when we use a distribution of sample means, that is the sampling distribution, we can apply what we learned from the last chapter, chapter 6, that is probability. And so the first thing we want to do, once we have, generated a distribution of sample means, is that we want to be able to find the probability that is associated with any particular sample mean. That is, hey, we want to compare the sample, specifically the sample mean, with the population mean. So we want to see where that sample mean is in relation to the population mean. So for example, here you see in the previous slide, we know what the population mean is, and we can use a sampling distribution of means to get the same value. Now we want to see where this sample mean is. Let's call this, M1. Where is that? And again, it's not scale. Where is this 101? I gotta be careful. I gotta draw on the right side. Wait a minute. There you go. Where is this 101.2? Is it really close to the population mean here? That is the same as the mean of sample means. Or is it far away? Well, we have a couple ways to tell. Well, we know the standard error in this sampling distribution is 3, so this mean itself is less, it's about a third of a standard deviation in the sampling distribution away or above the population mean. So once you know that, you can go, I know what the Z score is going to be. I know where that mean is in the sampling distribution, and I can start, figuring out how many people in the distribution are going to be above or below that mean, or what's the area between the population mean and that sample mean. So we can do all that probability stuff again with the Z table, because the sampling distribution is going to be a standard normal distribution that we work with. And so that way we can start comparing sample means with the population mean with the sampling distribution. Okay. So that's what we're going to do next. We're going to work with the unit normal table. We're going to get the Z score from the population mean, and then we're going to start finding stuff like the probability, its location, and so forth. So here's an example. This reads like SAT scores. You got your standardized score here, 500. You got a standard error here of 20. So if you get a score of 540, and when I say score here, I really should say sample mean, because this is now a sampling distribution. So everything under this curve is going to be means, sample means. So if you happen to find a sample with a mean of 540, then that's 2 standard deviations away from the population mean in the sampling distribution. So at this point, I'll also remind students, and that means you if you're watching, if you are a student, that once we have made a sampling distribution, you got to make sure you know which distribution you're working with. In hypothesis testing, we are testing with the sampling distribution. We're not testing with the sample distribution. No. We're not testing with the population distribution, because no, we can't get that either. So we are working with the sampling distribution. That's actually going to be the null distribution, which we'll talk about next chapter. So again, the sampling distribution, then the values in that distribution are sample means, not scores. And so if you happen to get a sample mean of 540, that is 2 standard deviations or 2 standard errors away. Again, got to use specific terms. 2 standard errors or 2 standard deviations away in this sampling distribution, away from the mean, above in this case. Okay. And the sample size here for this sampling distribution is 25. Again, you got to note several things when you do a sampling distribution. The sample size that you're using, the mean, that is the same as the population mean, and the standard error, which is the standard deviation of this distribution of sample means. And note that because it's a distribution of sample means, you're not working with scores anymore, not x's, but m's or x bars. So here is what you would do to get a z-score for sample means. Remember, in this chapter, we're no longer working with x's. We're working with sample means. As you do hypothesis testing, you will calculate sample means from your sample, so that will, apply all the stuff you learned in your previous chapters, like chapter 3 and 4 and whatnot, when we talk about central tendency and variability. But we're going to take that one step further and work with sample means. So in your formula sheet then, instead of saying x minus mu over sigma, if we happen to know the population mean and population standard deviation, notice here we're working with x. Now, if we want to set score for sample means, not raw scores, then instead of finding the deviation score or the distance between an x value and the mean, that is the population mean, we want to find the deviation score between the sample mean and the population mean, which we can calculate using the central limit theorem in the sampling distribution of sample means. Here, let me finish writing the mean word here. There you go. And then here, instead of using the standard deviation for the population in your z-score for raw scores, because we're working with the distribution of z-scores that has been transformed from raw scores, we are now working with standard error, because again, it's a distribution of sample means, not a distribution of scores. So therefore, the standard deviation underneath here is not the population standard deviation, but it's the standard deviation of the sampling distribution of means, or the distribution of sample means, which is standard error. So if you are asked to work with sample means, and if you're asked to find a z-score for a sample mean, you are working with a sampling distribution or a distribution of sample means. Therefore, you're going to get a z-score using the distance between the sample mean and the population mean divided by the standard error. So that is how many standard errors or how many standard deviations in the distribution of sample means is a sample mean away from the population mean. Okay, you're still using the same technique, but you're using different values now because you're working with a different distribution. That is the sampling distribution of sample means. So here's a picture of what that would look like. Again, you're looking at a sampling distribution. Again, this is not a distribution of scores, but a distribution of sample means. Notice here, you can tell because it's not x anymore, it's m. And so the values here are going to be means. In this case, then the standard deviation of this sampling distribution is going to be the standard error, not the standard deviation of the population. And so, yeah, this distribution, you can transform its scores into z-scores. And so a sample mean here of 525.6 would translate to, when we use the z-score for sample means, again, we use M for sample mean, and we use standard error because, again, we're working with the sampling distribution, not the sample distribution, not the population distribution. Then the standard error here would show us that a sample mean of 525.6 is going to be 1.28, plus 1.28. So the technique is the same, but you got to make sure you know what distribution you're working with if you're asked the z-score for a sample mean. You're working with a sampling distribution that has a population mean, but which is the mean of the distribution of sample means. It's going to have a standard error, which is the standard deviation of the distribution of sample means, and you're using sample means, not scores. The z-score is a location score that you're going to work with, and the distribution you're going to use is going to be a unit normal from the unit normal table, and then you can get probabilities and whatnot. So here you can see the middle 80%, that is between a sample mean of 474.4 and 525.6. That is between a z-score plus or minus 1.28. That's going to be 80% of the distribution. 80% of the sampling distribution is going to have a score between those two means. So here, let's do some learning checks before we end part 1. So question 1 here, multiple choice, population with a population mean of 60 and a population standard deviation of 5. The distribution of sample means for a sample size of 4 selected from the population would have the expected value of what? Again, you can pause if you want to, but you probably don't. Because once you know how this works, how a sampling distribution works, it's pretty easy. It's the same value. So it's the standard error that's going to need a bit more calculation. And that's where things get a bit more interesting in terms of, hey, you don't have to say, oh, it's the same number between the population mean and the mean of sample means. So question 1 is pretty easy. It says question 4, but this isn't question 4, this is question 2. So, true false question. A, the shape of a distribution of sample means is always normal. And B, as sample size increases, the value of the standard error decreases. Again, you can think about the properties of the sampling distribution, not sample distribution. You can think about the properties of this distribution of sample means, which is another name for the sampling distribution of means. Is it always normal? And think about how sample size is related to standard error. You can pause and think about this and write down your answers if you need to. So for A, the shape of the distribution of sample means, or the shape of the sampling distribution, is not always normal. If the sample size is large enough, and if the population distribution itself is normally distributed, then the sampling distribution is normally distributed. Remember, if we work with a small population and we work with a population distribution that is skewed or even symmetrical but not normally distributed, where the scores are no longer piled in the middle, or you get a small sample size of less than 30, then yeah, the distribution of sample means would not be normally distributed. And for B, yes, it's the law of large numbers, and we've seen it before. Since the sample size is the denominator in your standard error, then yeah, as n gets bigger, standard error gets smaller. Again, we've shown this with math, we've shown this with graphs, and again, you can review those graphs and math to see for yourself. Coming up as well, you're going to get the formula for the standard error, which is based on the standard deviation. Or yeah, it's the standard deviation formula, but with, again, values from the sampling distribution. So there you go. Before we talk about standard error and how we can use it to measure the variability of the sampling error, we'll end part 1 right here. So again, you would want to work on practice questions from your textbook as well as the web tutorials when it comes to seeing the properties of the sampling distribution of means for yourself. And you can get started as well calculating standard error if you wanted to, and also more importantly, getting z-scores in the sampling distributions. So keep going, work on those questions, keep practicing, and we'll see you in the next one.